Hello. This talk is about classical context-free parsing. The problem is very well known, so I don't think its statement is necessary here. Let me, however, begin with some quick standard definitions. I assume to be working with a fixed context-free grammar G, consisting of a set of terminals, a set of non-terminals with a distinguished start symbol, and a set of derivation rules, each turning a non-terminal into a sequence of symbols. For convenience, we denote the set of all symbols by S here. Now, recall the textbook construction of a pushdown automaton for this grammar. The automaton has a single state. Its stack alphabet is the set of symbols. Its initial stack is the start symbol, and it accepts by empty stack. It has two kinds of transitions, either reading nothing and replacing a non-terminal on top of the stack by the right-hand side of some associated rule, or reading a terminal and discarding it from the top of the stack. This PDA can be seen to operate in phases, each consisting first of some number of epsilon transitions, followed by a single non-epsilon transition consuming the next input symbol. In order to decide whether our grammar generates a given input string, we are going to conceptually simulate this PDA by computing the set of stacks possible after each phase. Each such set is a language over S. Note that these are languages of sentential forms of our grammar, and moreover, if we check the set of terminal words which can be derived from sigma sub tau, we will see that it is exactly the Brzozowski derivative by tau of the language we are parsing. Thus, at this level, our algorithm can be seen as a variation of parsing with derivatives or derivative grammars, representing the derivative languages not by grammars, but by languages of sentential forms. So, we process the input symbols one by one. The initial case is trivial, so we only need to derive the next stack language from the previous one. How does the PDA phase look like? We start with some stack in sigma sub tau and repeatedly apply rules to the leftmost symbol of the stack. The language of things we can reach this way, which we call the left linear closure, is denoted by square brackets here. Finally, we cut off the terminal by taking the Brzozowski derivative by it. For simplicity, assume for the moment that no symbol of the grammar is nullable. Then, the left linear closure must start with some symbol S on top of the stack, and, as the symbol cannot be erased, cannot touch what lies beneath. Moreover, the terminal we cut off must come from the left linear closure of S, as it is non-empty. Our formula turns to this. Now, to bring nullables back in, we can modify our PDA slightly. Whenever we are about to push some string sigma on the stack, we can immediately non-deterministically guess which of its nullable symbols are going to be erased in the future, and skip them right away. Effectively, we replace each stack language with what we call its nulling, denoted by the underline, consisting of all its words with each subset of nullable symbols removed. Our formula now turns to this. Note that this phase computation is phrased in terms of very simple operations. Set union, Brzozowski derivative, and prepending one of the languages in here. We call these the atomic languages of our grammar, and these can be computed when the parser is generated. Further, the number of these primitive operations in a phase depends only on the grammar and not on the input length. To complete the algorithm, we need a representation of stack languages providing the primitive operations. Here we go. Atomic languages are obtained by means of left linear closure and thus are regular. We will represent them by non-deterministic finite automata. To express the stack languages, we will use a DAG structure. There is a distinguished sinc vertex, and each edge is labeled with an atomic language or some its derivative. Now, with each vertex of this DAG, we can associate a language in the following way. We consider each path from our vertex to the sinc and concatenate the labels of all edges along it. Then we take the union over all such paths. Each primitive operation has a natural, straightforward implementation here. Importantly, we only add vertices on the left, never modify existing vertices, and do not ever introduce a cycle. This is in contrast to all prior general parsers, which often employ a somewhat similar structure, the graph-structured stack. And it will be very important for efficiency. If we plug this data structure into our top-level algorithm, we obtain a recognizer. Its theoretical complexity can be trivially shown to be worst-case cubic and quadratic when the grammar is unambiguous. Moreover, with a little more care, we can show the algorithm to be linear on LR regular languages. This brings it on par with the best-known generalized context-free parsers. To make our method more efficient in practice, we will take advantage of the repeatability of the stack languages. Let's say we are parsing some C-style language and consider the outline of some input source code shown here. Whenever we are between instructions in the same code block, the set of syntactically legal completions of the program from such a point is the same. But this set of completions is exactly what the stack languages capture. Therefore, we might expect them to repeat pretty often. If we make sure to never have two isomorphic vertices in our DAG, we can memoize the phase outcome for each encountered pair, consisting of a vertex and a terminal symbol. In our practical tests on Java programs, this eliminates about 90% of phase computations. And note that such memoization is already significantly stronger than what we get in other generalized parsers, as it can reuse results of computation at different input locations. It seems it could be added to some other parsers, but immutability and acyclicity of our DAG make it much easier and possibly also more efficient. It turns out that there is more repeatability to be exploited, not between the stack languages, but within them. This brings us to our second key contribution. Look at these two locations in our input source code. They lie at different nesting levels, and so the stack languages at these points are not going to be identical. However, what is locally syntactically valid at this position does not differ. The inside of the braces is in both cases separated from the outside, and thus valid PDA transitions cannot depend on what lies outside until the closing brace is encountered. To capture such situations more formally, consider a stack language which is factorizable, i.e., which can be expressed as a concatenation of languages of which the first is not nullable. Computing a phase from such a language does not need to look at the second factor. It can be treated as a kind of a context to be passed along, but otherwise irrelevant for the computation. The operation on the first factor can be memoized and reused even for a different stack language, as long as it has the same first factor. We call this technique context-free memoization. To detect factorizable languages, we enrich our DAG structure to keep for each vertex its immediate dominator. By this I mean the closest vertex lying on all paths to the sink. Acyclicity is a key feature which makes this efficient. We now keep each stack language in a maximally factorized form, as a stack of fragments between successive dominators. We also make sure that no fragment is nullable, except possibly for the bottom one. To compute a phase, we pop the top fragment and perform the standard computation just on this fragment. If the result is nullable, we combine it with the current stack top to keep the non-nullability invariant. Otherwise, we factorize it and push the factors on the stack. We memoize the mapping from the initial fragment and the current terminal into the sequence of factors we have pushed. How often is such memoization useful? On our Java corpus, in over 99.5% of all phases. So far, I have presented only a recognition algorithm. It is possible to turn it into a parser, and the basic idea is straightforward. Instead of just checking whether a PDA stack is reachable, we also compute how it can be reached. In place of stack languages, we now have relations between stacks and PDA transition histories. This is why we have called this algorithm relational parsing. There are two hurdles when pursuing this idea. The first is caused by nullables. Remember, we have simply optionally erased them from the atomic languages. Now, they cannot simply be forgotten because nulling them needs to be recorded in the transition history. Reaping the benefits of context-free memoization is even harder. It worked so well because reachable stack sets repeat very often. The ways of reaching them do not. They cannot even be independent of the input location. What does repeat is the functions mapping transition histories of one phase to those of the next. One can thus memoize the functions, still with 99.5% efficiency, and perform them once the end of the input is reached. For the details on both these issues, please see our paper, and the longer version of it soon to be pushed to archive. How fast is our method in practice? We have created a proof of concept implementation in C++ and compared it to what we believe to be the fastest practical general parsers available. YAEP, yet another early parser, LCount based on generalized LR, and Iguana based on generalized LL. We have used three grammars, two for Java, differing in the degree of ambiguity, and an unambiguous one for XML. Our input sets have a few million terminals each. Benchmark results are very promising. In recognition mode, we beat all competitors by a factor of 30 or more, and in parse forest construction mode by a few times. Most of the time in the latter case is actually spent not on finding the face-to-face history mappings, but on performing them. We believe this part of our implementation is suboptimal, and thus hope for even faster parser once we learn how to do it better. That's it. I hope you got at least a glimpse of what our algorithm is about. Thank you for listening.